Okay, everyone, welcome to our second condensed matter online condensed matter seminar this semester. Today, our speaker is Sayak. So Sayak get his master in science in 2015 from IIT India Institute of Technology at Kemper, and he got his PhD just last summer from Johns Hopkins University under the supervision of Professor Oleg Chernyshov. And Sayak's research interested mainly in theoretical condensed matter physics with areas including spintronics, magnetism, strong correlated system, quantum phase transition, topological states of matter, and ultra cold systems, etc. Um, so oh, I forgot to mention that after he got his PhD, he's now got landed a nice postdoc, joint postdoc position with Marcel France at the University of British Columbia and Masaki Oshikawa at the University of Tokyo. And I noticed some of Sayaka's interesting work when he was at Johns Hopkins. That was in close collaboration with an EFRC, right? The
Yeah.
let me see. It's the Institute of Quantum Matter, the
Yeah.
IQM. Okay, and he did some nice work on the spin wave modes in topological antiferromagnetic topological wire semimetals like in manganese silicon, manganese tin, sorry, right?
Tin and yeah, manganese tin and manganese.
Right, then this, you developed some field theory on the spin wave mode, right? It's,
Yeah.
and I believe that Sayak will tell us something about that. And now, without further ado, Sayak, please take it away.
Thank you, Shilay, for the kind introduction, and thank you for inviting me to speak at the CWRU Condensed Matter seminar. So, as Shilay pointed out, my current affiliations lie with UBC and University of Tokyo, but most of the work I'll be presenting here was done while at Hopkins. So let's get started. So basically, although I will eventually get to the field theory for the hexagonal antiferromagnets, which is what Shilay mentioned, I'll be starting off much slower. I'll try to introduce micromagnetism as a field theory in general, and then we'll actually study a slightly less complicated but very interesting system nonetheless, the XY ferromagnet, where I'll show that some phenomena that was pretty well understood might have some new features when viewed under this lens. And time permitting, I might get to some really interesting experimental / new stuff that we did on the manganese X systems. And I should say, if you really want, like, if you want any clarification at any point of time, just feel free to interrupt and ask the question. And I'll be available for discussions later as well. All right. So just to set some ground, in this talk, I'll mainly be talking about ordered systems, unlike most of the talks in strongly correlated systems where you would rather want to be near PC to investigate like interesting phenomena there. I'll be studying systems well below the PC, and these systems are ordered systems. And what I'll be mainly interested in is deviations away from the order. So the primary Hamiltonian that I'll be working with is the Heisenberg exchange Hamiltonian. And when you work with micromagnetics, you often don't keep the spins intact. What you would do is you would go to into a picture where you basically describe the local spins as magnetic moments, and they're connected through this gyromagnetic ratio, which is a relativistic factor. And usually you would do all your expansion in terms of this V over C relativistic factor that's present in the gyromagnetic ratio. Okay. So given the micromagnetic structure, the first question you basically ask is what are the energetics going to look like on this continuum model? So what we do is, again, we convert this spin into a magnetic vector, a unit vector, and then there are two kinds of energy densities that you can write down. You can write down a kinetic energy density, which is not really an energy density, and I'll elaborate on that. And you can write down a potential energy density. So potential energy density is kind of easy to write down. First of all, you want to maintain the overall symmetry, so it has to be rotationally symmetric because the Heisenberg exchange is rotationally symmetric. And you want to penalize deviations from a standard order. So basically, you end up writing the grad squared Laplacian term that you would write in spherical coordinates. In addition, in most systems that you would encounter in nature, you would also have some local lattice environment, and that modifies your energetics, and you would ad hoc, not ad hoc, but you would add symmetry dependent terms which incorporate this lattice effect into your energy density. So this usually comes in the form of a local anisotropy. It can be easy plane, easy axis, and actually a wide variety of these things. Now, the point about dynamics is slightly more difficult for spin systems in that spins don't really have an inertia. What they do have is angular momentum. So they're purely angular momentum states. They do not have inertial dynamics. And the best way to understand them is to through something like a gyroscope, where a gyroscope is just a purely angular momentum vector, and if you apply a force on it, it basically translates to a torque, which causes a precession through these equations. The same thing happens for spins, and that if you imagine a spin on some kind of M sphere, which is a unit sphere, and you apply, let's say, the equivalent of force for a spin would be a magnetic field, the resulting dynamics is purely precessional. Spins don't grow in length and they don't displace. They will just oscillate on the M sphere. And what you can do is you can modify these oscillations. And that's basically the kind of equation that you would extract out of Heisenberg equation of motion for these spins. Okay, so this precessional motion was summed up in the Landau-Lifshitz equation, which is basically presented here. Now, written in these terms, it's kind of hard to really do much to it. It's kind of hard to generalize it to a field theory. So we'd much rather modify this equation in terms of deviations from. So basically, although I'm writing M here, it's actually the deviations from the standard order that are meant here. You would reorder this equation in terms of something that looks vaguely familiar to a Lorentz equation. Okay. So if you recall, the Lorentz equation was just if you have a charged particle moving with velocity v in a force field, electric force field, you would feel a perpendicular Lorentz force. And you can see that this equation is analogous to what happens to a magnetization vector when moving under some form of an energy gradient. This picture is better understood pictorially if you basically map this magnetic field to the own magnetic moment of the spin itself, and you write down a vector potential that gives you that magnetic field. So what happens on the M sphere is that you have a monopole sitting at the center of the M sphere, and the tip of the charge, the tip of the magnetization vector is actually an electric charge that moves on the surface of the sphere. Now the only big problem with this construction, and this is typical to most gauge field constructions that you can have with these kind of precessional dynamics, including electrons, is that since you created a monopole and you described the whole system through a vector potential, you would need to compensate by putting a Dirac string of plus 4 pi charge somewhere, which basically carries away the flux generated by the monopole. And if you don't have that, you basically can't have this vector potential. So the vector potential that you will define on a sphere will always have this point of where it blows up. It's basically it's ill-defined at that particular point. By convention, it does happen to be that we do take this point to be either at the south and the north pole, but it basically could be anywhere where you can take out the string. I should say this whole picture was first formulated in one of Haldane's less noticed papers back in 1986. There's a more detailed review that I did along with my supervisor about 2 years back in this paper. Okay. So this analogy between electric charge and a particle in a magnetic field was capitalized on by Thiel. And what Thiel did was to write down an equation of motion which was exactly analogous to what a particle in a magnetic field would feel. Okay, so let's see what that would imply in terms of a Lagrangian. So if you have a massless electrically charged particle, the standard Lagrangian you would write down is this, and this. So there's just a standard potential. This would in general be an electric field, but it could be something else as well. You have a coupling to the magnetic field, and since I said that the spins do not have inertia, you would drop the mass term, the inertia term. Now, if you have a vector field that's pointing out of the plane, gz cap, with some strength g, which is basically related to the gyromagnetic ratio, but we'll not talk about that in much detail. What you see is that you'll get a set of equations that basically link forces to velocities through this ratio g. Okay. Now, the equivalent of that is something called a vortex, which is a unit charge in this magnetization sphere charge picture. And so if you apply a momentum to the vortex, what you would get is that this exact same copy of the equations that you had for the electromagnetically charged particles, but here now capital X and capital Y are the vortex center coordinates. And this analogy was noticed by Thiel when he wrote down these equations back in the 70s. And we'll see a much broader application of these type of dynamics, gauge type dynamics in general in ferromagnetism and antiferromagnetism.
Sorry, I had a quick question about your previous slide.
Yeah.
So I'm a little bit confused because I thought you were just talking about dynamics in a single particle, but then in this picture you seem to have reintroduced space as well, and it's become a field now.
For this guy or this guy?
For the one on the right.
All right. Okay. So basically, what happens is, and I'm hiding some factors here. The vortex will be, so once you have topological defects like magnetic vortices, you can move to things called collective coordinates, where instead of worrying about them as fields, you start worrying about the vortex as a single particle picture again, where basically you just concentrate on the core of the vortex as your particle, instead of worrying about the whole distribution as a field.
Yeah. Well, I just meant you were talking about a 0+ one-dimensional system before, and now it's right. You have a particle there, and here you have something that's got space in it as well as time.
This will actually become a little clearer when I do the full construction. This is just, for a moment, it's just an analogy that he wrote down. We'll actually introduce space-time properly a little later.
Okay, sounds good.
Yeah. Okay, so given the whole shebang, so the first line that I write down here is basically the Landau-Lifshitz equation in its full generality. You have the basically the torque here, and you have something called the spin transfer torque, which actually modifies to a convective derivative. And you can write down this whole lattice equation or this whole differential equation in terms of a field theory, where basically you have this vector potential now, which is this monopole created by the self-magnetization charge. And often what you would do is you would choose a spherical gauge for this monopole, where you pass your direct string either to the north and the south pole, and you would end up with a Lagrangian density that looks like this. Okay. One thing that I would point out at this point is that the Lagrangian density contains two factors. The cosine theta factor basically decides the spin density, and the phi is the azimuthal angle, and that is the main dynamical angle. So this coupling between the cosine theta and phi, which is like a conjugate coupling, so you can see the momenta of phi is cosine theta. If you calculate the Nernst momentum, is pretty ubiquitous in ferromagnetic systems. Just a point, if you want to have internal gauge dynamics, instead of doing this convective derivatives, the thing we do is basically change curvatures. And so we introduce curvatures and the gradients themselves. So for example, if you put your system on a curved surface, you would end up using something called the internal gauge for magnetism, and where basically the dm vector that we talk about shows up as a convective derivative. This point I will not come back to in much detail, but it's there for this curiosity's sake. Okay, so now I'll actually elaborate on Hirsch's point here and talk in some detail about the XY ferromagnet and the field theory of the XY ferromagnet. So the XY ferromagnet is basically pictorially just a combination of these two things. You have a gently varying spin texture on the XY field. So basically you have one independent angle here, the azimuthal angle, and you have topological defects called vortices and anti-vortices. Okay, so these are basically defects that are they are created in pairs, but after something called the Kosterlitz-Thouless phase transition, these pairs are no longer bound to each other, and you can have individual vortices. Now, given their structure, I would like to do something to the field here itself to show you that there is an underlying gauge field / underlying electromagnetism lying here. And so what you do is you take the standard structure of a vortex and anti-vortex. So vortex is basically, if you go around the vortex, the spin textures are winding in a clockwise, and if you go on anti-vortex, they're winding anti-clockwise. And if you take that field, that structure, so basically I write down the vortex field structure, the field distribution on the vortex. And if you do this transformation where you basically map del x phi minus del x y to an electric field in the y direction and plus del y phi to electric field in the x direction, you can see that this is a very familiar picture of a charge, plus a positive charge and a negative charge. So what you have is you can, under certain, like there's a construction out there where you can go from vortices and anti-vortices to a charge, to a plus minus charge in XY systems. And so let us build on that. This was noticed by Kosterlitz in a paper that eventually got him the Nobel Prize. And so let's elaborate on that a bit. So let's start off with the Heisenberg ferromagnet, and this is the lattice version of the Heisenberg ferromagnet. From here, what you can notice is that you can write down this term as a gradient term, gradient square term, and so that's basically, so from there we go into this continuum theory for the Lagrangian in 2+1 dimensions. So where you have the exchange term, which is basically these gradients, and you have an easy plane anisotropy because you want to restrict your spins to the xy plane. The kinetic term, as we noticed before, is given by this curious Berry phase term, which basically will, if you take this Berry phase term and if you integrate it around any loop on the xy plane, you will just get phi, because that's basically what the spins are doing on the plane. Okay. So how to solve for these vortices? To solve for the vortices, you take the exchange energy and you assume that your theta is in plane. And once you do that, you end up with something that's just penalizing your phi space gradient, and the solutions to that are Laplace equations. Apart from the trivial solution, which phi is just constant, the other solution that you can have is a vortex solution. And as I said, so you have a vortex configuration and an anti-vortex configuration, and both of them are basically characterized by something called vortex number. Okay. So once we have these basic ingredients in place, we'll again go to the limit where we don't really consider deviations from the plane, but at the same time, we just don't throw everything away, because it happens that often what happens at this stage is you just set theta equals to pi over 2 and just get rid of everything, and you end up with a very simplistic picture. We won't do that. What we'll do is basically a gradient expansion in the hard parameter theta, and we'll just throw out the space deviations of grad theta square, because basically we'll say that grad phi square is what matters, and theta really doesn't deviate that much from, let's say, a constant deviation. And once you've done that, the remaining Lagrangian that you have is this cosine, this Berry phase, the grad phi square here, and the easy plane anisotropy. And you can integrate out the hard mode by setting cosine theta equal to phi dot, which is basically the equation of motion for this. It's interesting to note that basically what I'm saying to this equation is that any deviations in the azimuthal field will lead to a canting spin canting out of the plane. And we'll come back to an important ramification of this later. Okay, now flying on, so what you get for the Lagrangian for the azimuthal field is just your standard wave equation type of Lagrangian. And this additional curious phi dot up in front basically characterizes an important aspect of vortex dynamics, and that vortex dynamics has this background magnetic field in which it moves, which leads to the Magnus force, and that basically is characterized by this extra phi dot that hangs up front. You can see that it has no effects on the equation of motion, but it does have an effect on, let's say, the overall Berry phase of the problem. So you can write down the equations of motion for this, and you will get a single polarization of the spin wave, and that's what you have in the xy plane. Okay, so now what we would like to do is to make more concrete the analogy with electromagnetism that we pointed out. So we are in 2+1 dimensions, and here we have electric field that's basically a vector, EX, EY, and a magnetic field that's a scalar. and this is the density that you're working with. You will have the Maxwell equations with the charge, and critically, you also will have the Bianchi identity, which is basically the statement that you can express this electromagnetic tensor as an exterior derivative of the gauge potential. And of course, since these charges are indestructible, you will have a charge continuity equation. And all of this results in a single polarization photon mode. We'll try to find these similar ingredients in our vortex theory and thereby identify what should be the electromagnetic dual of the vortex theory. Okay, so we're starting off with this Lagrangian. You can see that just by examination, we can introduce this B mu field, which we write down as the gradient of the phi azimuthal field. And this is basically Noether's equation, but it's also the conservation of spin current for our Lagrangian. Once you have this Noether's equation, once you have something that's basically conserved, you can see that we can write down this whole conservation equation to a curve. And this introduces our gauge fields. Critically, when you write down these conservation equations to a curve, we also impose the Bianchi identity that we want for an electromagnetic dual. We have already seen that the photon exists. So based from this equation of motion for the phi azimuthal field, so we have at least 3 ingredients satisfied here. We have a Bianchi identity, we have a gauge field, and we have a photon. Now for the matter bit, what you have to notice is the earlier point that we made was that in 2 plus 1D spacetime, you can also have these vortices which are indestructible. These are topological defects, and once created, the only way of getting rid of them is by ejecting them from the system itself. And these basically act as charges in our system. So if we put these charges together with the earlier,
so just to clarify, the magnetic field, because you mentioned you're working in a space-time, but the magnetic field, is it a scalar or a vector?
It's a scalar. So it's in an XY system, magnetic field is always like in 2 plus 1 magnetic field is always going to be a scalar. Okay. For it to get a vector notation, you would have to go to 3 plus 1.
And like like on the previous slide, so you're equating the red equation, you're equating B to the time derivative of a scalar field, right?
Yes.
So like okay, that makes sense. Thanks.
That point will actually be very relevant in a few slides down the line. We'll dump it. So basically we have found our electric charges that we needed to worry about, and that's these conserved matter, the conserved matter that we needed to form the electric charges, which is vortex density. And so we have the full shebang now that we need to create the duality between vortices and the 2 plus 1 dimensional electromagnetism. There's a cleaner way to look at all this, and that's through the differential forms in 2 plus 1 dimension. So let's just quickly go through that. And so what you have in electromagnetism itself is you have a 2 form, which is the electromagnetic tensor, and you have 1 form that is the conserved charge current. And expressed in differential forms, what they obey is something called the Bianchi identity, which is just an expression that the exterior derivative of the 2 form vanishes. And you can hence express the 2 form as the exterior derivative of some other field, because basically the square of something, the double exterior derivative of something is always 0. And then you can move to, then the other thing that you have is a Maxwell equation, which can be expressed as an exterior derivative of the Hodge dual field. And because you can express it like this, you also automatically get the continuity expression by applying another exterior derivative to this equation. And when we started off with the XY field theory, just from the field theory itself, we had sigma and j as 1 forms, and the conservation of spin was expressed through an exterior derivative of the Hodge dual of the spin current, and the vortex conservation equation is through the Hodge dual of the J current. It's a Hodge dual and not the current itself, because remember, we have to cross these gradients. We have to make del y phi into a del x and a del x phi into a minus del y. And so the duality map from just comparing these 2 sets of differential equations is that the vortex current maps onto the charge current electromagnetism, and the spin current maps onto the Hodge dual of the field density. Okay, so this is purely theoretical construction, and it need not like be visible anywhere, but there's actually quite an important ramification of this whole construction. First, we'll talk about just the plain charge theory and not involve magnetic field. So a very popular problem to study here is what happens when two charges, a vortex and an anti-vortex, annihilates. And there's a whole system by which you can analyze this whole annihilation process using just the Landau-Lifshitz equation on a lattice, like numerically. And you can see that I've basically plotted out some corrections. And so basically so you have some way of the energy leaking into the lattice, and these are through drag equations, which are called alpha terms. And these are all lattice corrections. So you have a mutual drag and a self drag and an edge correction. Okay. In addition to that, what you need to account for is the fact that these are charges rotating or charges oscillating in a dipole cavity. Okay. So that is best shown in this graph. So here the blue line is basically only frictional corrections from the cavity itself. So basically drag-like forces. But you also have to take into account that these are charges and they are basically stuck in this electromagnetic resonator, which is spherical. And so you can put in additional corrections coming from cavity resonances. And you do it in the standard way. You expand your vector potentials in terms of your Bessel functions, and you find out the amount of energy that leaks into these modes. And if you take into account those corrections, you get a much closer agreement with what the actual experiment or the simulations are done. Okay, so this is one aspect of just the charge factor. The second important ramification that we think.
Sorry, I had a very quick question about that.
Yeah.
So in your model, though, you don't have the viscous friction, right? You just have the radiation in the model as you presented it.
Right. So I basically buried the alpha term because it's like it's not something that's going to be mapped to a dual. You can add that through a Rayleigh term, but what this has the model that it has the radiative corrections plus the friction as well added to them. So you're seeing a double effect. So this is just friction, just alpha, just Rayleigh term, and this is radiative correction plus the.
Okay.
And also I should point out that this yet doesn't lie exactly on top of the simulation because we are just working to like the first two cavity modes. In like there is an infinite number of cavity modes you can couple. And so we are doing the very simple thing that just keeping the biggest contributions there.
So why is there so much scatter in the simulations? How are those done?
This is a package software, so I would really need to ask the undergrad who ran the simulations in Mumax or exactly why is there so much scatter. But yeah, it's not there's not much physics to be like have there.
Okay, that's fine. Yeah.
I have another question. What is the cavity that we're talking about? Where did the cavity come in? So
the cavity is basically this circular system. So basically, we have imposed periodic boundary conditions on a circular sample.
I see. So
this is the problem yesterday.
A disk of a magnetic system.
A disk of a magnetic system. So it's set to Fermi, but it really could be anything. Okay. So the part that I left out was what happens to these vortex cores, and it was like somebody already noticed that this magnetic field was related to the time derivative of the azimuthal field. And if you remember, the time derivative of the azimuthal field is also linked to the cosine theta, which is basically deviation from the plane. Now, even for a very strong in-plane anisotropy, there has to be at least one region in the whole system where the spins have to leave the plane, and that is at the core of the vortex. So if you take the electromagnetic map seriously, what it says is that the core of the vortex should carry a magnetic flux. And if you run with that kind of a assumption, or if you run with that mathematics, what it suggests is that vortices are not just charges, they are charge flux composites. And as was pointed out by Wilczek in the landmark paper in the 80s, if you have charge flux composites and if you take them around each other, you have basically statistics that might not adhere to standard boson fermion structure. Turns out for the vortices themselves, because they're made up of spin-half particles, we do expect them to just have bosons and fermionic statistics. But what will happen is most probably, depending on the inherent spin that's creating the internal spin that's creating the system itself will oscillate between a bosonic and a fermionic statistics depending on whether the internal spin is a 1 spin or a half spin. Okay. So from there, I'll move on to a different systems. If there's any question on the XY that needs urgent clarification, please ask now. Okay, so now I'll move on to a more generic spin wave theory. We are still going to stay.
I may have missed my chance, but can I ask a question over the XY?
Yeah.
So I was just wondering about like this, if the spins are integer, then you get a boson.
Mhm.
Is that obvious, or is it possible that there could be some kind of statistics transmutation, and that would be kind of amusing if that happened?
It would be very, we don't know, we are speculating here.
Okay.
All we know for sure is that it's charge flux composite and that you will get some noise, like there are some corrections to the statistics that will come from there.
Mm-hmm.
Now it's like, it is suggestive because of like, we don't want to say it's anionic or semionic or any like fancy things, but it suggested that it would go to bosons and fermions, but this is not known. We'd have to do a full quantum theory of the cores to really answer this question.
Yeah, I wasn't expecting that they might turn into anions, but I was wondering if you might get fermions with integer spin and, you know, bosons with half spin.
That's a possibility in these things, especially. It depends on so it basically depends on the composite spin of the core. And so it need not adhere to the same, so the composite spin of the core need not be the same as the spin that's creating the, that's the
right, that's what I was asking. Yeah. Okay, cool.
So let's move on. So we'll still stay in the 2 plus 1 dimensional plane for the moment. I'll drop the 1. So that's the 2-dimensional space plane, and we'll study spin wave theory for 3 sublattice antiferromagnetism. Okay. So now we go back to the lattice equation, and what I'll do is I'll quickly run through how you create one of these field theories in general, so that there's a recipe that's out there. So what you see is the first step of what you do to constructing these field theories. So first of all, you take your Heisenberg exchange interaction, and for antiferromagnets, you write it down as a sum over a plaquette, or basically the smallest unit cell of the moments involved in the magnetization. Okay. Once you've done that, your Heisenberg interaction basically forces the net magnetization to be 0. Okay. But you can have deviations from that. And deviations are characterized based on whether this condition is satisfied or this condition is not satisfied. So you have things called soft modes, where the overall moment per unit cell is still 0. And the Heisenberg interaction does not penalize these modes. And we have hard modes, which the Heisenberg interaction does penalize. And so we look into this in the simplest possible system in 3D, which is the two sublattice system. And so what you do is you have 2 sublattices, so M1 and M2. And so if you write down the Lagrangian for each of these individual sublattices in terms of the Néel vector field and the uniform magnetization vector field, you can see that basically see that the Lagrangian, well, it's not that obvious, but if you manipulate the Lagrangians in the correct way, you'll see that the kinetic term basically reduces to this kind of a term. Now for the potential term, if you write it down as sum of over the unit cell of M1 and M2 and expand it, you'll see that, again, as I said, the hard mode, which is the uniform magnetization, is penalized by the Heisenberg exchange, whereas the soft mode, the only correction will appear in the gradients. Okay? And so basic theory that we generate is something from just the Heisenberg interaction and the kinetic energy is a hard mode that's penalized by exchange and then corrections from soft mode gradients. And if you now write down, if you basically eliminate the hard mode from this equation of motion, we generate an inertia for antiferromagnets, which is not there for ferromagnets. So this is pretty unique. You will get the standard CK spin dispersion that you would expect for antiferromagnets. Okay. So what we want to get to is the study of the triangular unit, which is a bit more complicated in its structure. We do the same story. We identify the hard and the soft modes. The hard modes and the modes here, the best way, there are many ways to do this actually, and it's not a hard constraint, but it's best to expand your hard and soft mode in terms of the local symmetry allowed representations. Because it's a triangle, the local symmetry group is the C3 group, which is the rotation reflection group of triangles. And your hard modes are going to be ones that induce magnetization along the C axis, the eta axis, and outer plane. So these are your hard modes, and these are all C3 symmetric. And the soft modes are uniform rotations in plane, and basically rotations where you fix one of the spin as a rotation axis and rotate the other two spins above it. So these are your soft modes. Okay. So let's take a closer look at these modes in terms of a symmetry classifier. So you have singlet modes, alpha naught and beta naught. So in the C3 or the D3D system, what you have is you will have 6 modes, and you can classify the modes as a singlet mode and 2 doublet modes. So 2 singlet modes and 2 doublet modes. Singlet modes are scalars under the C3 rotations, and you have alpha naught and beta naught. And the doublet modes are basically vectors under the C3 rotations, and which I basically you can see it in this side of the panel, where if you take a beta x mode and you rotate it by 120 degree, it's basically a vector rotation, and it comes back to the doublet beta x minus beta y minus beta. So that's why it's a vector under these rotations. And the same for the alpha x alpha y mode. If there are chats, I'm not monitoring the chats, but if someone wanted to stand, please. Okay.
That's okay.
So okay, so now we can construct the full field theory. So first of all, we write down the kinetic term, again, in terms of the individual sublattices, and we express them in terms of these hard and soft modes that we wrote down earlier. And what we can see is that you'll always get this construction in which a soft mode will couple to its hard mode counterpart, because they are basically conjugate momenta of each other. And so you end up with a Lagrangian that looks like this. And your exchange penalties basically come in through the hard modes. So alpha x and alpha y were the hard modes in the xy plane, and beta naught was the hard mode for canting out plane. So the whole theory with just Heisenberg exchanges comes down to a field theory in which your kinetic energy is basically inertia terms you generate by integrating out the hard mode from the system. So you get inertia terms for the soft modes here for alpha naught and the beta doublet. Okay. So now we want to do the gradient corrections to this whole theory, and let's just take it one step at a time. And the good point about this whole breaking it down in terms of the local symmetry group is that now you're basically, as long as you stay within the manifold of Heisenberg interactions, your interactions will factorize into this form where you have interactions for the singlet and the doublet separately. You will not mix the two terms under Heisenberg exchange. Local anisotropies will indeed mix the two terms. So for the singlet mode, you have a very simple Helmholtz type equation, and this is a U1 degree of freedom. We'll talk in some detail about this later if I have time, but for now, it's just a simple Goldstone mode. Also, since you have a Heisenberg interaction, you have 3 soft modes. You also expect 3 Goldstone modes in your overall problem, in your spin wave problem. And so this is the first of the Goldstone modes. The field theory for the doublet is...
Sorry, I just got briefly muddled. Are we in 2 dimensions or in...
We'll always stay in 2 dimensions of space.
Oh, wait, two space dimensions, okay.
Yeah.
So then do you have to worry about, about the fact that you might have, like in the XY model, you get vortices and you don't really have an ordered state. Is that something to worry about here?
We do have to. In general, there can be, but we'll not talk about vortices in this model right now. So basically, we are trying to build that up to explain the magnetic structure of a material that has been studied, which has stable order. So there are not many vortices proliferating.
Okay.
Sorry. So the field theory for the doublet is slightly more interesting, and if you write down the gradient corrections, what you'll see is that there's a 1-to-1 correspondence between the spin wave theory for the doublet and an elasticity theory for the solids. Here, beta is basically the spin wave doublet that we wrote down earlier, And if you expand it in terms of the gradient expansions, with what we see is that there's a correction from something that looks like basically strains and something that looks like rotations. So the strains, you can find its counterpart in elasticity theory for solids. It's a linear strain. And if you just stick to these two, if you just stick to strain equation here and strain equation here, you can see the velocity of sound is replicated in the velocity of spin waves here. In addition, what you have for the spin wave theory for the doublet is something that comes from the rotation invariance of spins. In solids, rotations do not cost energy, but in spins they do, because the Heisenberg interaction is a dot product on the spin space. So you have this additional contribution from rotational gradients in spin space. So that basically modifies your sound velocity. So these are the two other Goldstone modes that you have in the spin system, and their velocities. So let's so let's study the triangular lattice, which is the simplest lattice on this model. We have the potential energy in terms of this. There's an additional, so since the triangular lattice is a highly symmetric environment, there's an additional symmetry that comes just from the fact that it's a triangular lattice. And so there's an additional enhancement of symmetry from just SO2 to an SO2 cross SO2, which is spatial plus the doublet. So SO2 from the doublet beta X beta Y, but also from the spatial symmetry group. And so what you have is a degeneracy between the beta spin wave modes and the alpha spin wave modes presented here. This was noticed way back in the 70s by Zytromsky and in Chubukov's and Subisa's papers back in the 80s. For the kagome lattice, things are slightly more interesting in that the kagome lattice has this extra factor in which one of its sound wave modes actually vanishes. It is exactly zero everywhere in the Brillouin zone. No matter, like it's not dependent on this gamma point field theory. Even if you do a lattice theory, you'll see that the sound wave is exactly zero. And this is analogous to this shear strain direction vanishing for the elasticity theory dual. Okay, and let me elaborate on this. So let me show you this a bit better. So you have an experiment here done by the group of K. Matana on the kagome lattice. And so what they observed was these flat modes that just span the whole of the Brillouin zone. You might ask, why is a Goldstone mode raised from the zero energy manifold? And that happens because of anisotropy interactions, basically the Yellow-Shinsky-Moria term. But you can see that this whole flat zone exists, and this is the flat kagome, or the zero flat kagome point. And what it means in terms of the spins is that if you look at the plaquettes themselves, you fix, let's say, the top spin of each plaquette, you can rotate the other two spins, and you can do that through the whole entire line without costing any energy in Heisenberg interaction. And that's basically the reason why these flat modes exist physically. There's a similar thing that happens in the mechanical lattice, and we expect that because of this elasticity theory dual, in which if you just have nearest neighbor springs, there is also a flat mode that exists in the lattice itself, and then just the mechanical kagome lattice. And this was pointed out in a paper by Levinsky and Mao. And it's a nice analogy that lies there. They attribute it to something called the Maxwell criteria, where lattices like the kagome are something called critical lattices. And it's essentially the statement of the same kind. Okay. A small note here, since we talked about duality a while back, there's also a duality that lies in the elasticity theory also. You can basically run through the same equation, run through the same motions that we ran through for the 2+1D system, and you can find out a dual theory for elasticities. And in that dual theory, what happens is that charges and dipoles are your basically the analogs of the vortices. This is a direction that we are currently also working on. So because we have something that's like the elasticity theory for the spins, we expect that this thing would also exist in the spin system. In particular, the interest stems from the fact that because there are it's a vector gauge duality and not just a U1 duality, we expect additional constraints, and that basically leads to something called Frappton dynamics. And so we'd expect the spin system also in the kagome lattice to exhibit some kind of Frappton dynamics. But I'll not elaborate on that. Okay, so now we move on to the final part, the manganese systems. So again, manganese systems are basically in line with the modern theme for studying physics, which is putting things on top of things. And so it's a stacked kagome. And so in this particular business, what we did was we collaborated with the neutron scattering group at Johns Hopkins, led by Colin Broholm, and they had done neutron scattering on these manganese germanium crystals, and then had extracted the spin waves. And our basic that was to calculate the spin wave spectrum and find out the exchange constants. And now we are dealing with a stacked system, although it's not rotated, but there's the additional complication that you need to now consider sets of fields from both the stacks. And the best way to do that for at least this system is to go to this basis in which you're considering symmetric and antisymmetric modes. So you symmetrize the modes from each layer. And these are the additional couplings, inter-stack couplings that we'll consider. So there is a J1 coupling between the between the opposite sublattices of the two stacks. So basically sublattice 1 of stack 1 links to sublattice 2 and 3 of stack 2. And J4, and this is antiferromagnetic, and J4, which is a ferromagnetic link between the two stacks with the same sublattice. Okay, now you can again write down the field theory in this whole combined scheme, and it's an absolute mess. But there's some order to all of this. You can see that the antisymmetric modes are all penalized by this J1, J4 exchange. In fact, there is a phase transition that happens when J1 is basically half of J2. J4 is basically half of J2, in which the stack becomes destabilized and you get spiral order in the system, and that you can see from this equation for C4 when this massive term becomes soft. And in addition, you can have the gradients as well. In addition to what we had as the quadratic gradients, because of the stacked nature, you have this linear gradient terms, which are linear in the gradient itself, but quadratic in the fields. And they are actually pretty obvious in the stacked systems. Okay. In addition, you also have to take care of the local anisotropy environments, and in germanium kind of environment, you have an easy plane anisotropy, which forces the spins onto the individual 2+1D stacks. You have a DM interaction, and you have an easy axis, which basically I show the easy axis in dotted lines here. It's to the nearest spin center. And if you write those down in terms of the field expressions, you can see I pointed out earlier that the DM interaction kind of bits the beta manifold, and that's basically expressed here. The easy plane does what the easy plane does. It penalizes all of the modes that lift spins out of plane. And the easy axis is a very complicated interaction. And in general, it will mix both the alphas and beta modes. Fortunately, in these samples or in these compounds in general, what happens is that the easy axis term is very, very tiny. Like it's like 1,000 times smaller than the DM, which is 10 times smaller than the exchange. And that pretty much rescues the situation and allows for a field theory description. But in general, this term will kill any grid, like in any gamma point physics that you have if it was large. Okay, so basically we constructed the models and we were happy with the models, but what turned out was a problem with the models is that when you do the spectral functions, we predicted large spectral densities at like finite energies for the 2 extra Goldstone modes, but apparently that is not exactly what we saw. So these additional humps here are not magnetic modes, but magnetism hybridized with phonon modes. And what we instead get is up in the high energy spectrum regions is something that is a combination of the two. And this is an indicator of a greater phenomena that maybe we'll get to in a bit. But overall, if you stick to gamma point physics and the modes near the gamma point energies, you can extract all the relevant interaction strengths. And as I said, you can see that thing that's noticeable here is that the easy axis anisotropy is really tiny compared to the other strengths. Okay, so since we have a C3 system, there are additional factors coming in from the C3 symmetric plane, which are not isotropic, but still you have to include them because it's just there in your field theory. And the way to write down C3 symmetric terms is basically to consider Ni as, so Ni are the vectors, the threefold rotation vectors in plane, and you can couple them to three vectors of your choice. So these are vectors under xy rotations. So for the scalar mode, if the only vector that you have is a gradient vector in plane, or the k vector, and the scalar is not a vector, so the only six-fold term that you can write down is this, and you can see that it will generate a threefold magnetic order. For the vector mode, for the beta mode, you have two vectors available to you. So these modes actually gain corrections to a lower order in K than the alpha mode. And so this is what would happen if you do it in the stack. And this is basically, so in the stack, you have now two vectors that come from the beta modes, one from each stack and one gradient mode. So you can reduce the whole K space dependence of the stack down to something that's linear in K. And this is basically the terms that we had earlier in the field theory. An important point that's still present for the kagome stack is that if we calculate with J1 and J2 and drop out the J4 term from the interaction, what happens is that you still have directions in K space where your modes are exactly flat. And they're exactly flat because although this term modifies the equations of motion and you still get something that is threefold symmetric, there are directions in K space it leaves unmodified. And you can kind of see that from the fact that if you just have J1 and J2, you still have these individual closed orders, where if you just consider an axis along the central point of the hexagon, you can still flip the hexagon about that axis. So you still have flat modes or flat directions along which you can disturb the order. Okay. Okay, so we can see how our external fields couple to under, what you have is in this picture is that you have a symmetric, you have basically C3 symmetric modes, and you want to study how external fields like magnetic field want to couple to the symmetric modes. And it's made easy for you because of this local C3 symmetry. You pretty much have to figure out what kind of vectors you can create from the C3 symmetric vectors that will basically either break time reversal or will break some kind of rotational symmetry. So for instance, if you want to couple it to an external magnetic field, the only time reversal breaking vector that you can couple to is this hard mode, which induces magnetizations. And R here is a rotation matrix in plane. So in general, you would have something like this. And you come to a feature on these compounds where the easy axis anisotropy, because of this coupling, has its own spontaneous ferromagnetic component. This component is very small in general for these manganese X compounds because this delta is tiny, but nothing prevents it from being larger in the other contexts. Okay, so I'm going to take a pause here and see if there are questions. The second part of this is slightly disconnected from the first one. Okay, so up till now, we have been basically talking about the magnetic structure of manganese X in general. The question now that we want to answer is that a few years back in the 2015 Nature paper, the group from ISSP, led by Satoru Nakatsuji, found that these compounds have a very large anomalous Hall effect. And then the question naturally arose is that what leads to this Hall effect signal, and B, can we change it? The what leads to the Hall effect signal was answered by Leon Berlentz and company, where they suggested that this Hall effect was due to viral nodes in the K space. And they basically gave an expression for the Hall conductivity in terms of this K vector. And the important bit is that this K vector is basically a vector in the XY plane, and it's directly proportional to the alpha naught mode that we were talking of before. So it's basically proportional. So the alpha naught mode that we had to the scalar mode for the magnetism in the Lagrangian lattice is directly proportional to this Hall vector in the system. And this was pointed out by paper by Jianping Liu and Leon Berlentz. In addition, what we know, and this is a kind of general lore in this kagome systems, is that there are states on something called a clock. Okay, And here I point out the alpha naught mode on the various clock states. The spins that have that are in blue are the states preferred by manganese tin, and the states which the green spins are pointed out are the states of manganese germanium. And you can maneuver within this clock through coupling to this K vector. And this is something that we try to do. We try to devise a plan of how we could basically flip from one of the clock states to the other clock state. What would happen is if you somehow manage to do this flip, you would also flip the Hall signal because K is directly related to the Hall potential. So what you can do is you can couple the system to a strain field. And what strain does is it induces, in addition to the easy axis that you had in the system, the strain induces another twofold rotation axis in the system. And the strain in this kagome type compounds can be broken, and in general in 2D systems can be broken into a vector, the pneumatic vector basically, where you can take the x and y components and form a cosine of the x component of the vector and the xy component on the y component of the vector. And this gives you an easy axis that's coming purely from strain. And so it would be really useful if we could couple this easy axis to our magnetism and basically use the strain to affect the alpha naught mode, which would then affect the Hall effect. And so that's what we figured out in this. This is still paper that's in the works. And so what we find that if we basically couple just the alpha naught, in plane kagome modes to the strain field, we can now go from a regime which is ferroholic regime, so basically where the Hall effect is plus to minus 1, and we can translate it to something that looks like paraholic and to diaholic. So we can flip the Hall vector sign by just changing strain. And this has, to point out, I'm not showing the slide for it, but this has been seen by Satoru's group, and we are currently working on a joint paper. The additional point about this is that when we do this flip, you flip the Hall vector slide, but you don't flip the magnetization, the mx-my magnetization that was ferromagnetic moment that was caused by the alpha x alpha y. That sign is not flipped, and this is basically a statement in that. So the local induced moments, they are modified by the strain fields here, but if you ramp through the strain vectors, you see that what happens is you decrease the magnetic moment and then you come straight back up. You do not change the sign of the magnetization, which proves that unlike common lore, the Hall vector is not just, at least in these systems, it's not just proportional to the magnetization. It's proportional to this K vector, which can be manipulated with strains and not magnetic fields. There is another set of interesting things that can be done, and I'll not go into details here because I'm kind of short on time, in that we can study structural phase transitions in the system also to the magnetic order, because structural phase transitions also couple in terms of the strains. And so this is currently work that we are doing, in which we can write down the Landau field theories for the coupled strains with this magnetic order and kind of figure out what kind of structural phase transitions that can happen. And we do understand one part of the whole story there, where we have a structural phase transition where that's second order, and what happens due to strain here is that the second order phase. So this is a phase transition from the A1G phase transition goes from uniform expansions of the lattice itself. So basically the lattice area distorts, the kagome triangle distorts in a uniform area. And that phase transition, what happens in the presence of strain is that the TC gets modified directly by the magnetic order. For the E2G strain, which is basically the deviation from uniform area, you get a slightly more complicated order parameter. It's a pneumatic order parameter hiding there, and we are currently doing MFT and RG, the mean field theory with the RG corrections to figure out the kind of effect magnetism has on that order. And this is still in the works. And so I'll leave you with that, and let me thank all my collaborators from the broader Institute for Quantum Matter, where we do all these collaborative projects. The strain details were done by the group at Cornell, Brad, Ramshan, and Pius. The Hall effect was done by ISSP. This is the theory proof by John Hopkins. And let me thank you for your attention.
Okay, thanks for the nice talk, Sayak. All right, any questions?
Sure, I had a question if I haven't already asked too many, which is, I guess it was more a comment about the kagome work that you described.
Yeah.
Kane and Lubensky also have a paper in which they discuss what happens if your kagome lattice gets slightly distorted.
Yeah.
And in that case, what they find is that, you know, depending on the distortion, they're topologically distinct. And so you can have edge modes, and it's kind of a mechanical topological insulator.
Yeah, yeah.
So I bet you could do that with your spin system too.
You can. So basically, there is I mean, I don't know if I can send you references, but there are papers in which there are spin metamaterials where you can have edge modes of spin for these kagome systems and for hexagonal systems in general. Mm-hmm. They have been constructed for just based on just classical spin. So nobody has done a spin wave construction here. Mm-hmm. There should be, because these are topologically protected modes. So by analogy, there should be equivalent edge modes here as well.
Any other questions from the audience? Yeah, I have one question. Could you elaborate the last part you talked about, the Hall conductivity, and could you elaborate a little bit how the magnetic structure, the magnetism, influence the electronic properties? Therefore, you can, you know, the position of the wire nodes relative to the Fermi energy, things like that, and therefore affect the Hall conductivity.
Right. So that connection actually lies in this when Lenz and Liu wrote down this expression. So it's basically the model that they have is some kind of an SD exchange model in which the spins hopping on the kagome lattice are basically connected to the electron. So the electrons hopping on the kagome lattice are connected to local underlying spin system. And if you calculate the Hall vector from this electron conduction bands, it turns out that this is exactly the alpha naught mode. So if you're doing a Hall effect from this symmetry point of view, you're trying to find out a vector in the Hall plane which breaks time reversal symmetry. And the only available vector in the Hall plane for these systems is basically proportional to the alpha naught mode, because that's the only U1 symmetric mode that exists in the kagome plane. So because the while in semimetal, the while points here are also confined to this XY plane, and you have, so for instance, the time reversal symmetry breaking Hall vector there would be the vector connecting the two while nodes. That would also be a vector in the XY plane. So you really can't escape this U1 manifold. All the U1 structures there have to be coupled, because most of the magnetism in these materials are basically through conduction electrons. They are not underlying, like they're not spin moments themselves. So if you're really somewhere that you can really look at the connection is this paper, but not in this paper. It's in the supplementary material of this paper.
I see. All right. Any other questions? Okay. If that's not the case, let's thank our speaker again, and we can have an informal session for the discussion. Right. Thanks. Let me stop recording.